That window gets out of the way. And let me just put the PPT back. I don't want this window here. This should go on the screen, and PPT is coming up now. And there you go. All right. I think we're good to start. A quick confirmation, Surabhi, can you see my PPT?
Yes. I can.
Okay, great, great. Super. Okay, thanks everyone for joining today's session. And this session is about Azure SQL Database Hyperscale. And just to introduce myself, my name is Balmukund. I work as a product manager with Azure Data. We take care of Azure SQL in general and hyperscale tier in specific. We are doing a lot of work behind the scene to make sure we are able to meet the ask from the customers about various features which they ask for, and we invest our time and energy in building those features. So I'm hopeful that in this session you will learn something new about Azure SQL DB Hyperscale. And in case you have any feedback, feel free to contact me now, or I'll put my email address in the chat window. You can use that later as well. So let's get started. The agenda for today is pretty simple and straightforward. We will talk about hyperscale. We will talk about the architecture of hyperscale, what exactly it is. We will also talk about something new which came up in hyperscale called serverless autoscale. And then I will also talk about what we released in recent past, right? And then some best practices about troubleshooting a problem which you might face in Azure SQL DB, stuff like that. I do not know whether people can raise their hand. If yes, just a quick show of hands if possible. Have you worked with Azure SQL DB? Yeah, I see Paresh hand up, but I think others may not be able to raise hands. Oh, they can. Okay. So how many of you have worked with Azure SQL DB? I see 1, 2, okay, 3, great, 4. Oh, wow. Okay. Wow. Okay, that's a good audience to have. So almost half of you have worked with Azure SQL database, which is good. And let me flip the question now. How many of you have worked with Hyperscale? You can lower the hand if you have not worked with Hyperscale. Okay, I see 3. Okay, 3 have worked with Hyperscale. Great. Okay, so I think this is a good audience for me. I can definitely make sure that you go here with by learning something new today, right? But those who know hyperscale will definitely understand something which is there in the background, which you have not seen in the public forum yet. So very first question, what is hyperscale? And the simple answer to the question is, it is a relational database in the cloud which uses the capability of the cloud, which is elasticity, which is one of the major thing which we get in cloud free, that your database would be an elastic database, which means you would be able to increase the size of the database whatever you want, right? That's the promise which comes from the cloud. But if you really look at Azure SQL database, right, it has the SQL Server engine which you have been using in the past. It is the same SQL Server code base which runs and powers these Azure SQL databases. So if I have to just summarize, there are multiple ways by which you can run SQL in cloud. You can run SQL Server in cloud in a virtual machine, which is called as IaaS offering. You can run, and then you can purchase a database in the cloud, which is Azure SQL database. And then if you want to have a complete instance in the cloud, then you go with Azure SQL Managed Instance. So these all comes under an umbrella, and we call it as Azure SQL. So when someone says Azure SQL database, they're talking about one of the tier of Azure SQL database. And you might also hear Azure SQL VM and Azure SQL MI. So these are the 3 flavors in which you run a SQL in cloud. Hyperscale is one of the tier in Azure SQL database. So there are 2 more tiers which you might have heard earlier in the past, which is called as general purpose and then business critical. These 2 are the 2 other tiers than hyperscale, and these all are vCore models. Like you purchase number of vCores, right? Now, as I said, this is the same SQL engine what powers the on-prem world as well. one of the big thing which hyperscale gives is it solves the problem what you have in VLDB. So imagine you have a multi-terabyte database. You have to plan for the backup. You have to plan for disaster recovery. You have to plan for its restorability, check whether the backups are valid or not. So there are so many complexity which comes with a very large database in the in on-prem world. That problem is solved by Azure SQL DB Hyperscale, right? It has a highly scalable compute and storage, and we will dig deeper into the architecture. Being in the cloud, and since it is a PaaS service, all you need to worry about is how to use the database. You need not worry about the admin overhead which comes with the database, right? And then it's an admin overhead, which means patching, installation, backup, and then storing the backups at some safe location. I remember a joke which someone told me that, sir, my server is crashed, my SQL is crashed. Okay, very good. Where are the backups? They were on the server, and then they lost everything, right? It's a good practice to keep the database backup outside the server. Don't keep it on the server. So if that OS crashes, you're doomed, right? And then Azure SQL DB Hyperscale, and I specifically call Hyperscale all the time with Azure SQL DB because people get confused when I say Hyperscale. There's one more product which is PostgreSQL Citus, which is also called as Hyperscale. So in this session, I will say when I say Hyperscale, I am referring to the Azure SQL database Hyperscale. So Hyperscale removes the limit which a cloud database might have, which is basically the size of the database, right? And if you look at the price per ratio, Hyperscale offers a good price per ratio for Azure SQL database. Right now, as I said, it is the same SQL engine, but just a managed SQL database, which means you don't manage the database management in terms of the admin work. You still write the procedure, you still write the code, you still use the database, you still do reindexing. So those are the things you need to take care. You need not worry about the size of the database, right? What size it is? Should I purchase new storage to get more database size and stuff like that? That's not needed in Azure SQL DB Hyperscale. So I'll just quickly, if you just take a moment to glance over the thing, you will quickly realize that whatever are listed here, they are the promises which are made by Azure SQL database, right? It is the same engine, as I said, which you have been using. You still use the same DMVs. Whatever feature you have in on-prem, those features are there in Azure SQL database as well. So it is not something new which you have to learn when you have to move your workload from on-prem to Azure SQL database, right? It has query store, it has adaptive join, UDF inlining. You name the feature. Whatever feature you have in on-prem, it is there in the database as well. Along with that, it has all the security features. It has same experience what a developer will do when he develops a software using on-prem SQL, right? And then it has integration with Purview and Synapse Link and whatnot. Now, whenever I talk to people about hyperscale, one thing which worries me is there's a subtle impression with the name that hyperscale is only for the large size databases, right? Which is a myth, right? Don't believe anyone if someone says I should not go to hyperscale because it looks like a big size. Unless I have a 20 terabyte database, 10 terabyte, I should not go to hyperscale, which is totally myth, right? You can always start small. So let's say you're doing a dev, right? You're developing the software and you want to use Azure SQL as a backend. Start with hyperscale, right? The advantage which you get as a part of hyperscale is there's a decoupling of the compute and the storage, which you see in the slide, right? So the application setting here, let me put a laser pointer, and I think this one is better. So this is the application which is what you write. It could be a web application or mobile application. It connects to a database, right? Now, as the database grows, if you're on other tier, you have to literally change the parameter for a database size, which is not the case with the Azure SQL DB Hyperscale. In Hyperscale, you just say how many vCores you want. You will not say what size of the database you want, because Hyperscale supports up to 100 terabytes of the database. And when I say 100 terabyte, it is not a hard limit that if you go to 101, it will stop working. That's not true. 100 TB is what we say is supported limit. We have tested, we have done enough testing with 100 terabyte size, and we have not seen any problem in terms of performance because of the large size of the database file, right? And as your application grows, right, you will see that we will start increasing the size of the database, like, automatically. You do not worry about the size. Now, when you are starting a application, you may not need, big database of multi cores. You might be okay with running with just 2 vCores, right? 2 vCore, 2 virtual cores. You provision a database, and then you start using that. And as the data grows, it will automatically scale, right? And then when you provision database, right, and when you have to scale a database from, let's say, 2 vCore to 4 vCore, it hardly takes 1 to 2 minutes. That's all. And this magic happens because of the decoupling of the storage with compute, right? So that's the advantage of having hyperscale. Now, other thing which come on, if I move forward. So if you look at the icon, I have increased the size of the icon. That says that you have increased the number of vCores of the database. It was 2, it became like 20 or maybe 40, right? And the new thing which has come in hyperscale is serverless. Serverless essentially mean that you are going to pay only for the amount of CPU you consume, not provision. So there are 2 kind of thing in Azure SQL DB. One is called a serverless, which means you just say min and max in hyperscale. I should be able to scale from 2 vCore to 80 vCore, 2 vCore to 40 vCore. But you will pay only for the consumption you did for the CPU on per second basis, right? It auto scales the CPU and the memory. You need not worry about should I start this application? Does it need 8 CPU? Will it go to 100%? Or should I go to 16 CPU? Will it be okay or not? No need to worry about those small things. Just say min, max, and that's it. Right? You have a hyperscale database. It will scale automatically in terms of CPU, in terms of storage. Everything is very good. Right? Okay. Now, ahead. Now your app has grown bigger, right? Let's say, now you think that now app is in production, people are using it. We should have high availability. Like typically in on-prem, you do always on or clustering and stuff like that. But here you will say, okay, I just need high availability. So what you will do, right? You will create a HA replica. You will add one more compute layer and say, I want a high availability replica. So in case something goes wrong, the primary, there is a HA replica sitting and waiting for failover to happen, right? So in case there is something which goes wrong with the primary compute, so I'm calling compute because there's a decoupling of storage and compute which you see here, right? This is the compute layer and this is the storage layer. So you will add a HA replica. So things are good, right? And then if you have to scale up further because now it is production, you can go up to 128 vCores in hyperscale, right? And then in hyperscale or any Azure SQL DB, you choose the amount of CPU, a number of CPUs, and based on the calculation of a factor, you will get amount of RAM or the buffer pool, and then you will get amount of local SSD cache on the compute node. So there are so many things which are calculated based on what you provision in terms of vCore, right? And then now you said, okay, I want cross-region GeoDR as well. So what you do, you create one more hyperscale in the paired region. And the reason we say paired region because the latency in paired region is typically very less. If you go to non-paired region, you might have a little longer latency in terms of asynchronous data movement, right? So now what you have done, you have increased the high availability. You have made a disaster recovery plan also just by a few clicks, right? You will not do installation of SQL and stuff like that. Just few clicks, and it will take care. Now let's say your app has gone bigger, right? And you are thinking now 128 CPU. are less. I want more CPU to be added. Now, every machine has a limit, right? It cannot go beyond a certain limit. My laptop cannot don't have the slot to put more CPU, so it will go to a limit. In that case, what you do? In that case, what you typically do is you basically divide the application into multiple portions, doing read write, doing read, doing analytics, and then you add something called as named replica. This is another feature where you define how many cores you want, and that's it, right? And they will be start using the same storage layer which you see here, right? So these named replica, what you see on the screen, are also computes which you will connect from the application and run the queries, and they will get the data from the storage. Now, how it works under the hood, I'm going to just cover in next few slides in the architecture slide, right? Okay, so far so good. Any question? Right now there are no question in the chat, so I'll move on. And then how many name replica you can have? The answer is 30. We have already done the geo replica, right? So now, now the next question could be, what kind of application should be using hyperscale, right? And one myth I already busted is that do not think it is only for the large size databases. You start small and then do a development, go to prod, keep scaling, upsizing, scale out. So those all things can be done. Now, if your application is a cloud-born application, right? If it is cloud, you definitely want a database in the cloud. You will not have an on-prem database talking to a application in the cloud. So and then if you do not know what is the number of CPU I might need, how much scale up I need to do, in those situations, you always go with the cloud based databases, cloud native databases, right? If you also have a workload pattern where you may want to have only 2 vCores, but my database size can go to 50 terabyte, you can always use hyperscale because there's a decoupling between the storage and compute. Unlike other tier, if you have to go increase the database size in business critical, for example, you have to increase the number of vCores as well. In business critical, the max size limit of the database is 4 terabyte, but to get the 4 terabyte, you need to have a certain number of CPUs. You can't have 2 CPUs in business critical with 4 terabyte. So if you have application which needs a decoupling of storage and compute, hyperscale is the tier for you, right? If you want fast scaling of the compute, let's say you want to go from 2 vCore to 80 vCore, it hardly takes, right? Your database will just grow in terms of CPU power, right? And then if you want read-write separation, you can have write on one compute, read from other compute. So that way you can have application doing both from the different machines altogether. If you want near real-time analytics, you can use, so let's say IoT devices, right? IoT device will send sensor data at a rapid speed, and the log generation, which means the amount of log generated by insert statements or bulk insert. We support up to 100 Mbps limit for hyperscale tier, irrespective of number of vCores. So you can have application putting IoT data, and then you want aggregation of the data, right? You can have a column store index and get the aggregated data in the near real time, right? ISV applications, few of our big customers are ISVs. They make their software as a service, and they use SQL as Azure SQL as a backend. And then if you want to migrate from anywhere to hyperscale, you are having on-prem or any other cloud, you are having a space crunch, you can always migrate to hyperscale. And then of course the data mart. Now let me with this all theory, let's jump into the architecture about whatever terms I used. They might be a little scary, but now things will fall in place shortly, right? Okay, so now one thing I've been telling, there is a separation of the storage and compute. So let's start from there, right? Here, what you see is the compute layer. P stands for primary. Anything what is coming from the application to do a write or read as well will go to primary. What you see in blue color is basically a cache, a local SSD cache, which is additional to the buffer pool, we also call it as a non-covering cache, which will cache the hot pages. So if there is a query which is asking a page which is used very frequently, we cache the page into the SSD. So you have a buffer pool and you have a SSD cache sitting on the compute node itself, right? And then if I move forward, red pathway, what you see is the log. So whenever the application writes something in the database, it has to generate a log record, and the log record has to be hardened somewhere, which is the typically LDF file. In if you remember the old, not old. If you remember the SQL on-prem world, you have a data in the log file. This is what represents the log file on the screen. So whenever you do a commit, it has to get a confirmation from the log service. We call it as a log service, and then only it will be committed to the client, right? Otherwise, we just wait. Now, what you see now on the screen is called as page servers. These are the set of page servers. Page server is chunk of the data file. So let's say your database size is, let's say, 512 GB, right? We create 128 GB chunk of the file, which means for compute, it looks like a one giant database, but in the background, we have multiple files supporting that database. So if you look at sys.database files, you will start seeing 128 GB each file, which are corresponding to a page server. This is where we get the elasticity of the cloud. As you can see that with this ... I can literally keep adding page server as your database grows. So you will not say, I want a 20 terabyte database. You will just say, I want a database with 10 vCores, and then you just start, right? Now, once you add more data, we'll keep adding page server, right? Now, these page server are actually the data residing place. Now, what you see in violet color, or whatever color you see on a screen, purple or violet, that is also a cache layer, which is sitting on the page servers. We call this as a covering cache. It contains the whole data file chunk, data file, what you have 128 GB in the local cache. If you take those small chunks of the local SSD cache called covering RBPX cache, that is actually the whole database, which is cached within the page servers, right? And then the source of truth, the actual data, is residing in the Azure standard storage, which is where our data files are. So now, whenever you see this 1 and 2, that represent there's a resiliency or redundancy in the page server, which means if in case there's one page server goes down, there's one more page server having exactly same data and which serve the request to the application. So there's a redundancy or resiliency at this layer here also. So that's why we have two data files, two copies of one file, right? Now, if I move on, you might wonder, where's the log file? That's the portion, what we call it as a log file. Log service does a process called as destaging, which is where we write the log file into the standard storage. So now imagine a situation where there's a crash of everything, every layer got busted, right? All those nodes went off. We have the data sitting in the storage, and we can always rebuild the whole system on just by this data file. So as you can imagine, everything is resilient. You will not have a data loss in case a primary goes down or a page server goes down or log service goes down. So everything is safe in cloud, right? Now, what you see on S is called as HA replica. They are called as high availability replica. They are the one who are secondary replicas for read-only purpose, right? They can read that they can serve the read request coming from the application. How you connect to them is you use the same server name, database name, and say application intent is equal to read only. That's the extra parameter you pass, and you will land up on the HA replicas. There you can run the read queries. We can have up to 4. Up to 4 means 0 to 4. If you are on the dev box or doing some work which doesn't need high availability, you are pretty much okay with just one primary. But if the primary goes down, we will spin up one more primary, and that remains primary till that crashes or something goes wrong there. But the advantage of having a HA replica is it is a hot standby. In case something goes wrong with the primary, we just fail over and secondary become primary, like always on availability. That's that. And then we have name replica, which I'll cover a little later. They're also compute. They're also number of vCores, but you have ability to choose how much compute cores you want on each replica. HA replica will have the same number of cores as the primary. So let's say your primary is 20 vCore, all the SSS, which is the HA replica, will have 20 vCores. Name replica is what a customer will decide how many they want based on the workload requirement. There might be analytical workload that needs 80 vCores or 128 vCores. So they will give a isolated name replica with a server name database name that will be there. They will connect and run the queries. So, and again, we take snapshot backup of the file. So the restores are pretty fast because we do a snapshot restore. We don't do a typical BAK and TRN and diff file restore, because imagine a 100 terabyte database backup and restore will take maybe days, but here it is max. What we have seen goes up to 30 minutes. Right? That's when we just, because they are snapshot, they are not literally the backup files, so that's fast. Now, log service, if I have to just cover in few minutes, whenever there's a commit coming from the application, it goes to the compute primary, which was P in the previous thing. There's a log writer thread, which basically writes the data to the primary replica of log service. Now, log service is, earlier we used to have something called as xlog, which was a single node service. As you can imagine, if there's just one copy of something that might have a scalability issues, it might have availability issues. So that has been solved by introducing log service. Now again, these all components are not visible to a user of the database. These are deep internals, but you should know that how it is working and how we are providing the resiliency and guarantee that your data is safe. Right now, with this log service, we were able to achieve few things. Right, low commit latency, which means earlier we used to take a little longer time to commit. Now this xlog sitting inside SQL process is basically a faster way to get the data committed, which means you get the higher IOPS. And as you can imagine, if we have to do a patching of this, we can, since we have 3 copies, we can patch one and still your app is available and everything is good. And this log service is just a SQL server. If you can imagine always on, it is just the always on secondary reading accepting the log, not doing any redo. Okay. So, and again, same as previous screen, these all log service will serve to the page servers, and then there's a long-term retention, which is data stored in the standard storage. And if you have other compute, the xlog will, or the log service will give the data to other compute as well by replaying the log and getting the latest data there. And whenever there's a write which you do, you'll start seeing write log wait, which is the waiting for the hardening of the log record in the transaction log, which is in this case log replica. Okay, I think someone's saying hello. Okay, I'll move on. No questions so far, which is good. Now let's dive into the page server, right? Page server is a component which hosts the chunk of the database. The chunk size is 128 gigs. So whenever you run a query to sys.database files from compute, it will look at the page servers. Okay, there are multiple files in the database, each 128 gigs, right? So this is what, and if you see, I have put one behind each other because there are resilient copy. There are 2 copies for redundancy for the page server. In case one page server goes down, there's one more page server which is sitting, which will serve the request. And by the way, these both servers work simultaneously, which means the compute will ask from the page server the quality of service check, whichever is good, having the good QoS, it will read from that replica, which is the point number 2 there, right? Each compute will have a blob under it, which is the actual data file, right? Now earlier, I think I will cover in the next slide. Earlier we used to have one-to-one mapping of the files, which means one page server, one 128 GB chunk of the file mapped to the Azure storage 128 GB, which gives the scalability issue, and we have solved the problem as well. So now what you see here is we make a smaller chunk of the 128 gigs file because we want Azure storage more files doing better IO than hitting throttling for just one file. And again, there's a SQL process which runs, and then yeah, it serves the long pages. There's a question. Okay.
Yeah.
The question is how much RAM compute in relation to vCore. The amount of buffer pool what you get is if I remember correctly, 5.1 times of the number of vCores in the standard series, and it is 10.2 times of the number of vCore in per vCore in premium series. So that's the calculation you can do, and the SSD cache is 3 times of the buffer pool size. So if you just put a number, 1 vCore, 5.1 GB of buffer pool, and around 15 GB of the RBPEX, which is the cache on computing. So and these numbers are available on, if you just search for vCore limits, you'll find all those numbers listed there. Yeah, they know to remember those numbers. I just remember because I keep telling everyone what the numbers are, but you can always find online. Yeah, don't need to buy hard those things. Okay, what is the purpose of the page server? It was the data file, as you can see. It also offload the checkpoint and the backups, which typically takes the compute cycle, right? So your compute is actually doing the meaningful work to run the queries, not spending cycle to do a checkpoint or take the back of the database. So that's a good thing which happens. And then storage, what we have under the hood, it will basically provide. We have option to provide you. Do you want a geo redundancy of the database file? Do you want a zone level or the local database file? So that's also available. So this is what I was saying in earliest architecture of our Azure SQL DB Hyperscale. You have multiple files, which if you look from compute, you'll find, let's say it is only 256 gigs of database, which means it will have two data files, right? So there will be 2 base servers, 128 gigs and 120 gigs. 128 gigs, both will be file ID 1, file ID 3, 2 is a log file, and then that will be covered by covering RBPEX, right? And that will correspond to one blob, 128 GB big blob in the Azure storage. We have changed this architecture because of the IO throttling which might happen with Azure, and we don't want to rely on just one file IO to get better performance. So what we have done this, right? Now one file which you see here is split into something called as multiple slices, right? And those slices can be on the same or a different page server. Each slice is now split into something which is 4 GB block, right? Now in this, one page server is actually one slice of the data, right? And then from multiple, now we are doing some work about having multiple slice of a different database into the same page server, which basically gives us better resiliency, and which also gives us an option to give multiple files in the storage. So in case there is some IO which we have to do, we will issue parallel IO to the files rather than doing one IO to one single file, which gives us better performance. Right? So yeah, as the slide says, it can do parallel seeding when we do a GeoDR, because now we have copy small chunk of file rather than 128 gigs of file. And the way we maintain this is basically using something called as map entries, which is listed here. So one replica will have a file name. It will have a slice of 128 gigs with the storage endpoint, right? And then other slice will be again 128 gigs. So there's the advantage of using this architecture. And again, this is under the hood, but you should at least know that there's enhancement which is there in the thing. What is the min time you can schedule snapshot backup to reduce data loss? Okay, there is no admin overhead on the customer. They need not worry about when the backups are taken. We take backups of the page server at regular interval, which may not be exactly same for all the page servers, and then we also take the log backups. So when you have to do a restore, we will take the snapshot which came just before the point of time. Those snapshot are, you can think that as a full backup, so to say. We just create new page server, attach this snapshot, and then replay the logs, because we do have snapshot backup and we do also log backup in the background. So so basically we replay the log to come to a point. When you do a point in time restore, we always come to the point when you ask for. So there's no data loss essentially which happens when you do a point in time restore. You have, yes, we do have point in time recovery. Yes. But by the way, I like your name. I don't know your name, but yeah, select no. Yeah, that's the answer. CheckDB, we do periodic CheckDB. You can also do CheckDB if you wish to, but yeah, there is a housekeeping which we do on the databases by running CheckDB. Yes. Okay, now how do we read a page, right? We said there's a compute, there is a RBPX, there is a storage. What exactly happens? So this is that blob storage, right? We spin up the first time when we spin up the page server, we seed the page server, right? And this is asynchronous, right? So when a new node comes with a page server, we basically do we populate the RBPX cache with by reading data from the blobs, which is an Azure storage, right? And remember, I said everything crashes, and when we start everything afresh, this is the flow. What happens, right? So we warm up the page server in the layer there, and then when there's a primary or secondary which also has RBPX. Now this RBPX will be warmed up by the ask of a page. So now let's say there's a page which have been asked by a query. If the page is there in the RBPX, which was a hot page, we will do a hit in the cache, and then that page will not be read further from the page server because it is in the local non-covering RBPX cache. If there is a cache miss or RBPX cache miss, then we run something called a function called get page at LSN, and then we ask from the page server that give me the page for this LSN. If the page server has the page on the LSN, it will give the page back to the compute. Here's the page. If that page is not, if the page server has not caught up on the LSN, it will go to log service. Can you replay the log till this LSN so that I have the latest copy of the page, and then it will serve the request, right? And so when you read from the compute RBPX, the latency is like 0.5 to 2 millisecond. There's additional hop if it has to happen. It will be it will be like 2 millisecond again. Now, if whenever this happens, when you're reading a page, what do you see in the query wait stats? It will be shown as page IO latch wait because it is trying to read a page. So you'll start seeing the page IO latch in the sorry, in the queries which are running, right? They will wait on page IO latch. All right. Now, as I said, there's something on read scale in Azure SQL DBA-VUG Hyperscale. This is the HA replica, and this is just to recap what we have learned about read scale. So this is HA replica, which is same size as the primary compute, and these are the name replica, which can have its own size in terms of the vCore. You can, let's say you have a 2 vCore primary, 2 vCore HA, and then you want 80 vCore node to run analytical query. You spin up a name replica, and then you take it from there, right? So name replica are for read scale, and this all has to be in the same region, right? If you want to run an application query from a different region SQL server, SQL database, you create a geo replica. That way you get the data there, right? That's the geo replica I was talking about. All right. Name replica, just to recap, these are the name replica on the right hand side. They take data from the same set of page server, same set of log service, which means if you remember always on availability group, primary talks to secondary, which is not the case here. Primary doesn't talk to secondary. Log service is the one who will talk to the compute and give the data. And if the page is not there, it will go to page server and get the page, right? So again, these are SSD cache, which is non-covering because it is not full set of database. It is only hot pages cache there. This is the covering cache, which means complete 128 gigs is cached in this thing, right? These are the read-only copies of the database, which you can have your own size, independent of vCore, and then they has to be in same region. They cannot be in different region, but can be on different logical server. They can have their own logical server. They can have their own database name also. But again, they are just the logical entities. The actual data is still on the same set of page server. We support up to 30, and then we support isolation of the read, which means you can create a login on the compute of the name replica and use that for the application. And that's the command. And I think we will share the video so you can look at the command later. It just so the only thing is we say secondary type is named. That is a name replica. If you put geo, it is a geo replica. That's how you create them. You can use T-SQL, REST API, PowerShell, all 5 methods to create. Failover group, which is also a GA feature now. In failover group, basically, if you really see, we have an endpoint, a listener endpoint, which you connect. So there's a primary region, which has DB1 and DB2, and these are the HA replicas. If you want copy of a database across the region, in a different region, you can create a geo secondary, and then if you want the same connection string to be maintained, irrespective of the role of the primary secondary, you will start using something called a read-only listener or read-write listener. In case of failover, application need not change, and they will continue using the same name. What is listener endpoint, and the request will transparently be sent to the primary or secondary, irrespective of where they are running, right? And now, if you really see this page server, every region has its own page server. They are not cross region. A region has a set of page server for a database. So that's GeoDR. Failover groups gives you an extra layer of multi-database failover, right? GeoDR is per database. When you group them together as a logical entity, they become a failover group, and what you get additional is the endpoint, right? Then there's something called as zone resiliency, which is multi-AZ. So in Azure, if you really see, within some region, we have multiple zones, which means multiple data center within the same region. Let's say, for example, East US. Let's say East US supports multi-AZ, which means East US region will have 3 data center with a few miles apart, which will have their own power supply, own air conditioning, and everything of that sort, so that in case one zone goes down, still you have database sitting in the same region, right? And with the log service implemented, now we can support multi-AZ for Azure SQL database Hyperscale as well. Only thing you need is one HA replica. So if you really see, there are 3 zones here: zone 1, zone 2, zone 3. And all the layers I've separated. Compute, you have one primary, one HA in 2 zones. Log service has 3 replicas, so we keep them in separate zone. Page server has 2 copies, we keep them in separate zone. Now imagine a situation when zone 2 has to go down. HA replica on zone 3 will become primary. We will spin up one more HA replica in zone 1 probably, and log service will fail over to zone 3 or maybe zone 2 because they're zone 1 because they're alive. Zone 2 is dead, and for page server also we have copies. So essentially, if you see, there is no regional failover which you have to do. You still remain in same region. There's no failover which you have to do for the database for GeoDR, right? So that's multi-AZ feature, which is there in Hyperscale. And let's move on.
Hey, Balmukund, just a quick reminder on time. We have around 6 minutes left.
Sure. Yeah. Okay. Cool. Let's quickly talk about serverless. Right. Serverless is a new offering which is there in Azure SQL DB Hyperscale now. And I think I briefly explained what serverless is, but just to give a complete story, right? Let's say you have an application, right, where or you're starting a new application and you do not know whether you need 8 vCore or you need 2 vCores. You're not sure, right? Because you can't provision that. So what you will do, you will essentially say, I could be anywhere between 2 vCore to 8 vCore. When the load comes, you scale up to 8. When the load goes down, you scale down to 2 vCores, right? And so you basically define min and max of the vCore in Hyperscale. And this serverless feature is there in the general purpose tier already, where we have auto pause facility where the data will be paused after an active period, which is what you see here. So basically here the database was scaled up, it came down. 1 was the min number of vCore. The database stayed below min vCore for a certain amount of time, and then it became inactive. And then once it is inactive, we will just pause the database. When we say pause, there's no billing which runs on the database. You don't pay anything for the database except storage. And then once the database wakes up by the application connection, we start the database just like that, right? So that gives you more price and perf optimized solution using serverless. So that's one is scaling and one is billing. The only thing to keep in mind is the billing happens on per second basis, and if you ever compare the price, the per second pricing is costlier than provision because of the various things which happen behind the scene. So if your application has a constant workload of certain number of CPUs, provisional might be a good fit for you. The rule of thumb says. Rule of thumb is if your workload, if 50% of the time you're not hitting your max workload, max CPU limit, then you might try serverless and see whether you can save some more cost there. Now, what is not there and again, it all depends on the usage pattern of the application. What kind of application will start using serverless? Few who do not need a lot of CPU, what you provision, and then fresh databases where you do not know the pattern of the application, those will typically use that. And again, it is fully transparent for user. You need not worry about HA and DR and stuff like that. Everything is inbuilt, right? So what we have in serverless is basically this, right? It is so as of now, what we do not have is auto pause, but we have auto scaling, right? Which means you can always scale up to 80 vCores, right? Not till 128, that will come in future. So you can always say, I want to scale from 4, let's say 10 vCore to 80, because my workload might spike up to 80. It needs 80 vCore at some point of time, but not all the time. So I will not provision 80 vCore. I will let it go to 80 and come back to 10 whenever it feels like, right? As I said, GP general purpose also has this serverless feature, but again, the performance-wise, Hyperscale is much superior than general purpose because general purpose has totally remote storage. There's no RBPX and stuff like that. And as you can see, the advantage of this is we have name replica. The auto scaling happens irrespective of CPU and the memory, because you might need more CPU at certain point of time. And again, it's billing per second, whereas in provision storage it is per hour, basically. Right? And I think that's all the theory I had to cover. I think I have 2 minutes more to take more questions, if any. Otherwise, I think we are pretty much good. I can just cover a few preview features. One is premium series, which I said earlier. If your application is memory hungry, it needs more CPU, more buffer pool for same number of vCores. You might want to try this because it gives you double the buffer pool for the same number of vCores. The price is higher for the premium series, which is memory optimized. So there are two flavor of premium series, right? If I just go on the slide here, if you see, right, there are two premium series. One is memory optimized, which can go up to 80 V core, which has more memory. For the same number of V core, you get double. So I said earlier, 1 V core 5.1 in premium, 1 V core 10.2 buffer pool in memory optimized. Right. So I think, yeah. Other thing is short-term retention, more than 7 days. Long-term retention up to 10 years is there in the public preview. So if you have a database and hyperscale, you can go ahead and try those features. And this is a few list of customers who have been successfully using hyperscale. There are case studies available. If you just go to customer.microsoft.com site, you should be able to read those stories about how they have become successful by using various features of Azure SQL database. And this is one more list of customer. And then I think that's all I have. In case of any question, please feel free. I can take it up.
Surbhi, you can stop the recording now.
Yep.
Thank you, Balmukund.